All right, now that we're all in an excellent mood, we can tackle some trig identities fun. Definitely fun. Our learning goals, we're going to learn what it means to prove a trig identity, memorize the basic identities, and by memorize, really just be able to reference to them, and then build patterns for solving more complex identities. As I've mentioned, you're watching this for one of two reasons. You're just curious, you're like math puzzles, you want to see what this is all about, and or you are planning or would like to keep the door open to planning for taking grade 12 advanced functions. Which again, as I've mentioned, if you're taking grade 12 advanced functions, you definitely want to watch this and you definitely want to try some of these without looking them up on the internet, because when we get back to the building, hopefully next school year, you're going to have to do these. And these are the simple ones, and when you get to grade 12, you're going to get way more advanced. So we're going to start with a warm-up to kind of show you what it means to prove something. So we want to quote-unquote prove that the equation below is equal. Oftentimes you would do like a left side, right side check, something like that, or you might have to solve an equation. I have two different things, two different expressions, one on the left, one on the right, and we want to prove to see if the left side actually does equal the right side. So we would do some mathematical operations. We would distribute first. On the left is 2x plus 16 minus 6. I'm just going to stick to one side right now. And then 16 minus 6 is 10. 2x plus 10. Now switching gears to the right side, distribute 2x plus 10, 2x plus 10. Hey, I got the exact same thing on the left side and the right side. So left side equals right side. We're not going to bring things over to the same side of the equation, because if you did that, you would just get 0 equals 0. We're not solving an equation. We are proving something. That means that for any value of x, plug in any number into x. The left side will always equal the right side. The best way that I can describe identities is that it's a puzzle. Sometimes puzzles are frustrating, sometimes puzzles are easy. One thing is for certain though, if you give this your honest try, anyone will admit to you that when you figure out how to solve a puzzle without looking it up, you feel good about yourself. And yes, you might have, some lows and some downs where you don't feel good because you're so frustrated. But once you figure it out, you have this euphoric feeling. It feels good to solve puzzles, to figure things out. Your goal is to get left side equals right side. You are searching to rearrange or substitute or some other algebraic operation that does not, so that's the key there, does not change the value of any of the arguments. Arguments are just pieces of the expression in the original equation to make a statement of equivalence. Left side equals right side. Nothing ever crosses the equal sign. We are not solving. Nothing crosses the equal sign when you're proving identities. What you are doing is you are essentially decoding a hidden message or puzzle. So we already know the left side equals the right side. We already know that there's going to be the left side expression is going to equal the right side expression. But they look different. So you have to change them, rearrange them, augment them, manipulate them to look the same. These are some general steps. They're starting points. They're not necessarily universal, and the only way you get better at these is practicing. So step one, typically we start with the more complex looking side. Not always, but it's usually a good idea to change everything so that it's in terms of sine and cosine. Memorize the basic identities, which I'm about to give you on the next slide or slides. If you have to deal with fractions, you have to make common denominators. And then practice, 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 and then practice more. That is the only way to get better at these. Before I give you some of the identities, some tools in your toolbox, I want to go over one common error. It's very, very similar to what an error would be I try to get you to avoid for the rationals and radicals unit. I think we said that it was when you made this mistake, I said you were killing bunnies or killing kittens or something. If you have 1 plus sine x over sine x, you cannot do that. That is bad, and say that equals 1. Very, very bad. Actually, I'm going to put x's for the i's. Cannot do that. If you're multiplying, you can do that, but if you're adding or subtracting, you can't do that. And remember, to give you a very simple example, if you had 1 plus 2 over 2, you wouldn't say that equals 1. It actually equals, right? It actually equals 3 over 2. So don't do that for sure. The first identity I'm going to give you is the quotient identity. Now, sometimes I will prove or explain why these work. For the sake of a virtual lesson, I'm not going to bother going through that proof. But if you want to know, you can message me and I'll go over it with you individually, or you could look up why it works. So tan x equals sine x over cos x. There is your first tool in your toolbox, if you will. The reciprocal quotient identity, cotangent x, cotangent, right, is just the flip of tan. So the flip of sine x cos x would be cos x over sine x. And if your intentions are to try some of these on your own, which I challenge you to, you might want to write these on a separate piece of paper so that way as you go through the identities, you have like your toolbox sitting in front of you and you don't have to flip through your pages to find it. The next one is the Pythagorean identity, which comes up a lot. And it looks like Pythagorean theorem. And what it is sine squared x plus cos squared x equals 1. Now, just so you know for notation, whenever you see the squared like that, that is the exact same thing as that. The reason why it doesn't go on the outside is because, so I guess we'll write this as an aside. The reason why this doesn't go on the x is because if you were to write this, that tells me to square x and then take the sign of it, but I don't want to do that. I want to take my final answer and square it. So these two things are not equal. Little sad face. But getting back to the Pythagorean identity, sine squared x plus cos squared x equals 1. If you rearrange that, I can move the cos squared to the other side and becomes 1 minus cos squared. I could rearrange it with moving the sine squared, and it will become 1 minus sine squared x. Those are the next 3 tools in your toolbox. The reciprocal identities, well, we just did those in the last lesson, so they're not new to you, but cosecant x equals 1 over sine x. Secant x equals 1 over cos x. And cotangent x equals 1 over tan x. So those are the only tools in terms of like formulas or identities, conversions, if you will, that we're going to use in grade 11. And then you're going to see a lot more in grade 12. So here we go, our first identity. We want to prove that that equals that. Again, nothing crosses the equal sign. We need to rearrange, manipulate, substitute to make one side look like the other side. And so you know, there are an infinite number of ways to get the left side to equal the right side. Some of them are the road less traveled, to be the equivalent of like if you were to drive from Simcoe to Dover, but you drove from Simcoe to Edmonton to Chicago to Dover. It works, but we're not going to do it. So there are an infinite number of ways. Some are long, some are short. It doesn't matter how you get there. All that matters is that you get there. So we're not bringing anything across the equal sign. You also can't just plug in a value for x. So we know this is true. So if you're thinking, well, I could plug in 30 for x and do cos 30 times tan 30 divided by sine 30. Yeah, that's 1. You've only proven it for 30 degrees. You haven't proven it for any possible value of x, and that's our goal. So let's get at it. First thing, left side and right side. You got to tell the reader which side you're working with. One of our tools or one of our ideas, our steps, was make things in terms of sine and cos. Okay. Tan, I know tan is sine over cos. So all I've done is substitute what I know tan is. Tan is sine over cos. That's one of our tools in our toolbox, the quotient identity. That is convenient. I have something on the top that is same on the bottom. Those cancel. So that leaves me with sine x over sine x. Whoa, anything divided by itself. You can think of it as canceled. Anything divided by itself is 1. We got 1 equals 1. Left side equals right side. So to finish this off, you would say left side equals right side. Therefore, proven. And be proud of yourself. We proved our first identity. And we are going to do a bunch, just so you know. Prove cos x equals this. Let's start on the more complicated side, which looks like the right side, and convert things to sines and coses. Okay, so work on the right side. Not going to touch that. Tan, I can convert to sine x over cos x. Okay, so far so good. And then where do I go from here? Well, I would multiply this, right? Negative sine x times sine x would become anything, right? X times x is x squared, y times y is y squared, sine x times sine x is sine squared x. I have fractions, okay? I have a common denominator. They both are over cos x, so I can make this 1 minus sine squared over cos x. 1 minus sine squared x, that's one of our Pythagorean identities. That's cos squared x over cos x. Cos squared divided by cos, the squared cancels out that one on the bottom. You're just left with cos x. And if you need a refresher on that, it's like if you did x squared divided by x, the squared cancels that one out. You're just left with x as an aside. Left side equals right side, right? We got cos x on the left side. Therefore, proven. And we're happy. Next one. Prove left side equals right side. There's different ways you could take this, just like all of them. You could start with the right side or you could start with the left side. Just to change it up a little bit, instead of changing tan to sine over cos, let's see what happens when we work with the left side. If you're adding something and it's over a common denominator, you can split it up, basically working backwards from what we just did in the previous example. So I could split this up into cos x over cos x. plus sine x over cos x, right? That's a common denominator, and if we were to combine those, we would have it over 1 cos x. Cos x over cos x, that's just 1, right? Sine x over cos x, that's our quotient identity, that's tan x. Left side equals right side, right? That's the right side. You could have started by changing tan x to sine x over cos x, and you would have got to the exact same result, but different steps to get there. Therefore, proven. Wink, a frowny wink, whatever that means. I don't know. That's just what I happened to randomly draw. Our next one. Ooh, this one looks intense. Okay, where to start? Well, both sides look kind of complicated. I might have to work on both sides. Let's see what happens. Let's start with the left side. I need a common denominator. Okay. That means I need one of those guys and one of those guys. So I need a 1 minus sine x and a 1 plus sine x. That's my common denominator, which means this gets multiplied by this, which is just 1 plus sine x times 1 is not going to change. This gets times by this, but don't forget about that negative sign. Okay, so negative and then 1 minus sine x in brackets. Distribute that negative through 1 plus sine x minus 1 plus sine x all over. Now, let's FOIL the denominator to see what happens. So we're going to FOIL this. First times first. 1. Outside, sine x. Inside, negative sine x. Last terms, minus sine squared x, right? Negative sine x times positive sine x is negative sine squared x. Collect like terms on top. Well, 1 minus 1, okay, they're gone. Sine x plus sine x gives me 2 sine x. At this point, it's looking promising because I have a 2 on the right, now I have a 2 on the left. Collect like terms on the bottom. Plus sine x minus sine x, they're gone. So 1 minus sine squared x. You could stop at this point if you wanted to and work with the right side. But let's keep going. 2 sine x over 1 minus sine squared. That's one of our Pythagorean identities, which is cos² x. We could switch gears and work with the right side, or we could keep working with this side. How could we work with this side? Well, what if I wrote it like this? Instead of cos², just cos x times cos x. Those two things together, what do they make? They make tan x, right? Sine over cos. So that's 2 tan x over cos x. That's our right side. That's that. Left side equals right side. Therefore, proven. So we didn't even have to work with the right side. But you could have if you didn't realize. But again, a lot of these things you're probably going to be asking yourself, like, why did he do that? And there's not necessarily a right answer or a why. It's just something I tried. I tried a puzzle piece, tried to fit it into a spot. It either worked or it didn't work, and I had to regroup. But practicing makes perfect. I'd be lying to you, as would any math teacher, be lying to you, even a mathematician, that you could throw any trig identity in front of them and they instantly know how to solve it. They'd be lying. I'd be lying to you. That's not the case. Sometimes you try things, and sometimes it takes me, 4 pieces of paper of attempts to get somewhere that I think is good. So this is one of those things where it is like a puzzle, and puzzles can be frustrating. and you can go in different directions. And just like if you've ever built a puzzle before, and if it's one of those like Ravensburger, like 10,000 pieces, and the pieces are incredibly small, sometimes it helps to walk away and come back and take a look when you've cleared your head, cleared that frustration. Our next one, tan² x plus 1, prove that it equals secant² x. Let's start on the left side. If tan is sine over cos, tan² is sine² over cos². So we can change tan² to be sine² over cos² plus 1. I need a common denominator, which means, how can you change 1 to be a common denominator of cos²? It just simply has to be cos² over cos², right? Anything divided by itself is 1, so cos² over cos² is 1. Okay, we have a common denominator, cos² x sine² plus cos² on top. That's your Pythagorean identity. Sine² plus cos² is 1 over cos². You could keep working with the left side. Maybe let's show some love to the right side. It's really only one more step. Secant is 1 over cos. So secant² is 1 over cos². Left side equals right side. Therefore, proven with a big happy smiley face. Done. How are we feeling so far? Are we rattled? Feeling okay? Maybe we could try a little bit by ourselves. Let's see. So like I said, I do have lots of examples for you. This is a little bit longer, but just to show you as much as I can possibly show you. F, prove this. Okay. Well, let's convert things to sine² and cos². So left side equals secant² is 1 over cos², cosecants 1 over sine². I need a common denominator, which is 1 of both those things, which means that times that, which is sine² x, that times that, which is cos² x. Sine² plus cos², Pythagorean identity, 1 over cos² x, sine² x. Now, if you're thinking, well, wait a minute, on the right side, it's got sine in front of cos. Remember, multiplication does not matter the order. So that is, in fact, a left side equals right side situation. Therefore, proven. Smiley face with the tongue. Double exclamation. G. If you're thinking to start on the right side, there technically is nowhere to go that you know of anyway. It already is sine x, it's already cos x. So that means we have to start with the left side. Cotangent, that's 1 over tan, yes, but it's also, in terms of sine and cos x over sine x. And cosecant is 1 over sine x. Now this is going to happen a lot, especially in grade 12, where you got fractions and fractions. It looks rattling, it looks confusing, but trust me, you can deal with it. You just got to stay organized. Also, if you're someone that likes to fit everything on the same line of your line paper, so you make your fractions like this with like a backslash, I would abandon ship on that and go outside your comfort zone and just use 2 lines to do something like that. Anyways, looking at the top, I need a common denominator, which would be sine x. So what do I change the 1 to? Sine x over sine x, right? Cos x over sine x, all over 1 over sin x. Working with the top, you have your common denominator, sin x plus cos x over sin x. Now, one thing you have to remember this middle fraction line really is just divide. When you divide fractions, what do? Your rules are to change it to a multiply. I'm going to write a dot for multiply just because we have x's, and flip the second fraction. When you divide fractions, going back to like grade school, when you divide fractions, you flip the second fraction and change it to multiply. So flip the second fraction and change it to multiply. Well, that works out really well for us because I have something that's the same on the bottom as the top. They cancel. I'm just left with sin x plus cos x over 1, which is just sin x plus cos x. Left side equals right side, therefore proven. H. Prove left side equals right side. Okay. This is a good one. A lot of fraction work here. Let's start with the left side. Cos x minus 1. 1 minus secant is 1 over cos x. I need a common denominator on the bottom. That 1 would just change to cos x over cos x minus 1 over cos x. Which that would change to cos x minus 1 all over cos x. Then do not forget, remember that's dividing, so you change it to multiply. I'll put a dot for multiply, and you flip the second fraction. So that would be cos x over cos x minus 1. Now you have something on the top and bottom that's the same, they cancel. You're just left with cos x. Same idea, more or less, with the right side. Cos x plus 1 over secant 1 over cos x plus 1. That's going to change to cos x over cos x plus 1 over cos x plus 1 over cos x plus 1 over cos x. Invert and multiply. Flip that second fraction. Same on top and bottom, they cancel. You're left with cos x. Whew, that was a good one. Left side equals right side. Therefore, proven. We are geniuses. Yes, I went through that quickly. Yes, it perhaps is made to look easy or easier than it is. But again, rest assured, it takes lots and lots of practice. I prove 1 minus cos squared x equals sin x cos x tan x. This one's not too bad. You probably could tackle this one on your own. 1 minus cos squared, that's one of our Pythagorean, right? So that just equals sin squared. If I look at the right side, let's change our tan. So sin, oops, don't need that line. And tan is sin x over cos x. Those cancel, top and bottom. So all you're left with is sine times sine, right? Which is sin squared x. That was an easy one. Too easy. Therefore, proven. You want one more? Let's do one more. We're going to make it a tricky one. I look at that and it doesn't look like there's anywhere to go. Everything is sines and coses. We could change signs, like we could do our little fraction trick, I guess, and write sin x over 1 plus cos x, and that's not going to help either. Abandon that ship. So here's where sometimes things really blow minds. As long as you don't, so you remember from one of the very first slides, our general steps, as long as you don't change the value of the expression, you can do whatever you want. And it's kind of like when you are simplifying a radical to get it out of the denominator. You're changing how it looks by multiplying by something over itself, which anything divided by itself is 1, so you're not changing the value. We're going to do that for this question, something like that. And if you're wondering, how do I know to do this? You don't. It's just a tool in your toolbox if it looks like you can't do anything else. And again, just coming from lots and lots of practice. All right. If I were to multiply by the conjugate, so 1 minus cos x over 1 minus cos x, let's see what happens. And again, I'm not changing the value because I'm multiplying by something over itself. Distribute. Okay, that's sin x and negative sin x cos x. And do the same thing on the bottom, FOIL this time, right? First comes first is 1, outside, negative cos x, inside, plus cos x, last, minus cos² x. Well, that's good because those cancel. Negative cos x plus cos x, they're gone. So on the top, we have this, and on the bottom, we have this. Let's common factor out of sin x, which would leave me with 1 minus cos x. And the bottom is your Pythagorean identity, sin² x. We're basically there. Sin x cancels out with one of my 2 on the bottom, and that leaves me with 1 minus cos x all over sin x. Left side equals right side, therefore proven. Maybe we'll make this your mind being blown. Maybe, hopefully not. Either that or you have a giant piece of broccoli on your head. That concludes your kind of bonus, optionally mandatory trig identity lesson. Like I said, if you're taking advanced functions in grade 12, I have a handout for you. It has some solutions, plus you can look some things up online. I can also post some questions from the textbook for you to try. You would not be doing yourself a favor if you didn't try them at some point. So you don't have to try them before your test. I don't want to interfere with that, but you should try them at some point while it's fresh in your memory over the next few days, I would say. Again, looking them up on the internet is not going to help you. Looking up the solutions I posted are not going to help you. If you get stuck, then yeah, have a look. But copying down, word for word, step by step, what you see online or in the solutions is not going to help you practice the strategies you need to solve identities. With that, we are done Cartesian trigonometry for now. We will be coming back to trig at a later time, working on trig functions, so graphing trig functions, sine and cos. So you are aware, if you're watching this lesson, the next time we are together, it's just a quick 2-day week. 4 lessons, 4 formulas, 2 days. You're gonna see. I'm gonna have it where there's 3 on one day, 1 on the morning of the next day, and then your test that afternoon. You could choose to watch a lesson or 2 on the night before, and then that way you only have 2 or 3 to watch on the first day, and then you'd have the whole morning to study on the second day and then do your test on the afternoon of the second day. So the next unit after this, quick, short, sweet, 2 days, 4 lessons, 4 formulas. Normally you have to memorize the formulas. Obviously you'll have them at your fingertips. Hopefully it should be a mark boosting unit for those of you that want to boost your marks. That's it. Thanks for listening. Good work, everyone, sticking with this unit.